All right, so have you ever tried, like, describing where your house is, but you can only say the street name?
Oh, I see what you mean.
Yeah, like it's on Street 2. It's not very helpful, is it?
No, not at all. There could be tons of houses on that street. You'd never find it.
Exactly. Or imagine like a dot on a completely blank piece of paper.
Okay,
Or if
yeah.
you just say like it's somewhere near the top, that doesn't really tell you much, right?
Yeah, you'd be searching forever. And it's really interesting, right? For so long, that's kind of how we had to navigate the world.
It's true. We had pretty vague ways of describing locations for a really long time.
Yeah, it really puts into perspective how important this idea of coordinate geometry is. Like, it seems so simple, but it's really a big deal.
Huge. And that's exactly what we're going to be diving into today for you, like all those basic ideas of coordinate geometry. We've got this chapter all about it, and what we really want to do is, break it down and show you how we went from those kind of vague descriptions to actually being able to say exactly where anything is on a flat surface.
Right. It's such a fundamental concept, but even these basic mathematical ideas, they have such a massive impact. Like in science, engineering, you name it.
Yeah, totally. And it's everywhere. It really is. So, okay, let's go back to those kind of frustrating scenarios. Like
Right.
that house on Street 2, even if you know it's number 5, if you only had the street, you'd never find it.
Exactly.
And this chapter actually has this really good diagram. Like, imagine a grid of streets, right? All numbered running east-west.
Okay. Yeah.
And then the houses are numbered along avenues that cut across them north-south.
Okay. So like a grid system, like a city.
Exactly, like a city. And there are like 2 houses marked. One is H, and it's at like Street 2 and number 5.
Okay.
And then there's P, which is at Street 7, number 4. They're both clearly defined.
I see.
But the key is you need both pieces of info to find them.
That's a really good illustration of the core idea here. You can't just have one piece of information if you want to find a specific spot in 2D space. You need like two separate things.
Exactly. One isn't enough.
Nope.
And so what about, remember that DOP on the paper we're talking about?
Yeah, yep.
Like saying it's in the upper half or near the left edge. Like that just, it doesn't tell you anything useful.
Right. It could still be anywhere it's not fixed.
Not fixed at all. But then what if we say, okay, it's 5 centimeters away from the left edge?
Okay. That's getting more specific.
Yeah, we're narrowing it down, right?
Yeah, but you still couldn't, like, put your finger on it, right? It could still be anywhere along that line.
Yeah, you'd have a whole vertical line of possibilities.
So then the question becomes, what's the missing piece? What else do we need to know?
Right, and this is exactly what the chapter gets into. Like, you need another reference point, another independent measurement.
I see.
And that's where it gets interesting, because then they add, and it's 9 centimeters above the bottom line.
Uh-huh. Now we're talking.
Now we have it. Like, boom, suddenly we know exactly where that dot is.
Yeah, it's the intersection, right?
Yep, the intersection of a horizontal line at 9 centimeters up and a vertical line at 5 centimeters from the left.
Perfect.
And the chapter really emphasizes that point. We needed 2 independent pieces of information to lock down the location.
That's a really clear way to put it. And this leads to a really nice way to formalize the idea.
Exactly.
How do we take this idea, this intuition, and turn it into a system that always works, you know?
Right, and that's where this seating plan activity they talk about comes in.
Oh, interesting. Tell me about it.
Okay, so imagine a classroom, right, with desks all arranged in neat columns and rows.
Yeah, classic classroom setup.
If you're sitting in the 5th column and the 3rd row, well, we can show your position as 5-3.
I get it.
The column number first and then the row number. So here's a question. Is 5-3 the same as 3-5?
Ah, that's a good point. And this is so important to remember. Order matters. If 5-3 means you're in the 5th column, 3rd row, then 3-5 would mean you're in the 3rd column, 5th row. Totally different desk.
Completely different desk. Like, this really simple activity just drives home how crucial that order is when we're using 2 numbers like this.
Yeah, and if you mess up the order, you end up in the wrong spot.
Exactly. The chapter gives this example. They say Sonia, who they label as S, is in the 4th column, 1st row. So they write that as S41.
Makes sense.
The S is for Sonia, and that ordered pair 4-1 tells you exactly where she is in the whole seating plan.
Very clear. So we've got this idea of 2 reference points and the fact that their order really matters. But how do we take this from a classroom and apply it more broadly?
Right, and the material credits this guy, René Descartes, who was a philosopher and a mathematician. It says he was actually just resting in bed when he had his big aha moment.
Wow, that's amazing. Like, so many groundbreaking ideas come from these, like, everyday situations.
I know, right? It's so cool. So he figured out this system of using 2 perpendicular lines to pinpoint the location of any point on a plane.
And it's a development of a much older idea, the idea of latitude and longitude. You've probably heard of that, right?
Oh yeah, for like locating places on Earth.
Exactly.
So it's all connected.
Yeah, and what blows my mind is how this seemingly simple idea, like needing two pieces of information, leads to such a major breakthrough. And they named the whole system after him, the Cartesian system, or sometimes it's called the coordinate system.
That's so cool.
And he really changed the game. Because of him, we can turn geometry into algebra. This really shows how powerful abstraction is.
So cool. Okay, we have this idea of two perpendicular lines. Let's get to, the actual construction of it.
Yeah, let's do it.
So the chapter explains how you build this Cartesian plane, and it starts with taking two number lines. One is horizontal, and they call that x is x, and the other is vertical, and that's y, y. Each one of those extends infinitely in opposite directions from their 0 point, and each one follows the usual conventions for positive and negative numbers.
Okay, yeah.
And then, the key part, you got to make those two number lines intersect, and they have to intersect right at their zeros.
Oh, I'm starting to see. So that intersection point.
That's the origin, and they use the letter O for that,
Cool.
right? And from there, the horizontal line, XX, becomes our x-axis.
Okay,
And the vertical line, YY, becomes our y-axis.
makes sense.
Now, positive x is to the right of the origin, so that's labeled OX, and the negative x direction is to the left, labeled O-axis. Same idea for the axis. The positive direction goes up from the origin, labeled OY, and the negative direction goes down, labeled OY.
So it's like those are our starting points, right? Like the edge of the paper or the columns and rows we talked about before.
Exactly. They're our main reference lines.
That's a good way to think about it.
And then we can't forget the origin, O. It's at the 0 point on both axes, so its coordinates are...
Perfect.
So now we have our axes, but they're not just sitting there. They actually, divide up the whole space.
Oh, yeah, that's right.
They split the entire plane into 4 sections, and those sections are called quadrants. And the way they're numbered is important. They start at the positive x-axis and go counterclockwise.
Counterclockwise, okay.
So first you've got quadrant I, then quadrant 2, then 3, and finally I.
Got it. I remember back in school having to memorize all the quadrants, and yeah, counterclockwise was the key.
It's a standard. And, in things like statistics or physics, dividing the plane into these quadrants can really help with organizing data.
Yeah, it helps you categorize and analyze things more systematically.
Exactly. Okay, we've got our grid, but now how do we actually pinpoint, a specific point on it?
Good question.
And this is where coordinates come in. For any point on this Cartesian plane, you can nail down its exact location using two numbers.
Okay,
Its x-coordinate and its y-coordinate.
I see.
Now, the x-coordinate, they also call that the abscissa, and it basically tells you how far the point is from the y-axis. It's the distance measured horizontally.
You can also think of it like the point's shadow on the x-axis if you were shining a light straight down on it.
Ooh, that's a good way to think about it. And so if it's to the right of the axis, it's a positive number, but to the left, it's negative.
Makes sense. And the y-coordinate, right?
Yep, that one's called the ordinate, and it's basically the same idea, but in the vertical direction.
Right. It's the perpendicular distance to the x-axis. So if it's above the x-axis, it's positive, and if it's below, it's negative.
Exactly. And remember how we were talking about order mattering with the seating plan?
Oh, yeah.
Well, the same thing applies here. When you write coordinates, you always put the x-coordinate first, then a comma, then the y-coordinate, and you put it all in parentheses. So it looks like this, xy.
And most of the time, xy is going to be a totally different point from yx. Unless x and y happen to be the same number, of course.
Right, exactly. And the chapter actually gives us a few examples to really illustrate this, so let's walk through them.
Okay.
They've got this point labeled B, and they show that to get there, you move 4 units to the right along the x-axis.
Okay, so the x-coordinate is 4, right?
Yep. And then you move 3 units up parallel to the y-axis. So the abscissa is 4, the ordinate is 3.
And the coordinates of B are?
Perfect. Nice. And then they've got this other point, M. This time you go 3 units to the left.
So that's a negative x-coordinate, right?
Right. So x is -3, and then you go 4 units up, so y is 4.
And the coordinates are?
Exactly.
Cool.
And there's point L. For this one, you go 5 units left, so x is -5, and then 4 units down, so y is -4.
So L is at 5?
You got it. And lastly, there's point S, and to find it, you move 3 units to the right.
So x equals 3.
Yep, and 4 units down, so y equals -4. That puts S at 3, negative.
Makes sense. And, walking through those examples, it's a great way to see how the signs of those coordinates tell you which side of each axis the point is on.
Right, exactly.
Positive or negative, it makes a big difference.
Totally. And then the chapter moves on to another example that specifically looks at points that are right on the axis.
Okay, so they're not in any of the quadrants.
Exactly. Like take point A, it's at 4.
Okay, it's on the x-axis.
Right. It's 4 units to the right, but it's not up or down at all. So its y coordinate is 0.
Gotcha.
And then there's point B, which is at 0, 3.
So that one's on the y-axis, right?
Right. So the x coordinate has to be 0, and it's 3 units up, so its y coordinate is 3.
Cool.
And then the rest of the points follow the same pattern. C is at 5, 0.
5 units to the left, no vertical movement.
Exactly. And D is at 0, negative 4.
No horizontal movement, 4 units down.
Perfect. Even point E, which is at 23, 0, follows the same rule.
It's on the x-axis, so y is 0, and its x value is 2/3.
Right. So you see a pattern here, right?
Yeah, it seems like any point on the x-axis is always going to have a y-coordinate of 0, and its coordinates will be x 0, 0. And then for the axis, it's the opposite. The x-coordinate will always be 0, and the coordinates will be 0, y.
You got it. And of course, the origin itself, since it sits right on both axes, has coordinates 0, 0.
Yeah, that makes it like the ultimate reference point.
Totally. And then to really tie everything together, the chapter gives this really useful summary of how the signs of the coordinates relate to which quadrant you're in.
Yeah, that's a handy trick to remember.
So in quadrant 1, both x and y are positive, so it's like plus plus.
Okay,
In quadrant 2, x is negative and y is positive, so it's
plus
on your.
quadrant 3, they're both negative, so
And finally, quadrant 4 is plus and minus because x is positive and y is negative.
perfect. So just by looking at those plus and minus signs, you can get a pretty good idea of where a point is on the plane.
Exactly. It tells you which quadrant it's in.
Very cool.
And the chapter also makes this kind of interesting point about the XY convention itself.
Well, what's that?
Like putting the abscissa first, then the ordinate, it's just a convention. Like we could have easily gone with EX instead.
Yeah, we totally could have. It's kind of arbitrary, isn't it?
Right. But the XY way is what everyone uses now, so it's important to stick with it to avoid confusion.
I agree, and this just highlights how important it is to have those standardized ways of doing things in math and science. It keeps things clear and consistent for everyone.
I agree. Standardization is key. So, you see, we started with this, this simple problem. We just wanted to be able to say exactly where something is.
Yeah, it's a problem we face all the time.
And it led us to this really elegant and powerful system.
Exactly.
And it might seem kind of abstract at first, but this whole idea of the Cartesian plane and using coordinates is just like super fundamental.
Yeah, it is. And if you think about it, this system is kind of hidden behind so many things you probably use every day.
It's true.
Like mapping apps, right? Those rely on coordinates to show you where you are and how to get places. And then, like, computer graphics. Every single pixel on your screen is defined by its x and y coordinates.
It's everywhere.
It really is. It's the language we use to describe and analyze spatial relationships, and we can be super precise about it.
Yeah, super precise. Okay, so just to recap the key takeaways from this deep dive into coordinate geometry.
Let's do it.
We saw how needing two coordinates isn't just some random definition. It's really the key to being able to represent the position of anything uniquely.
Right.
And we explored the Cartesian plane, which is formed by those perpendicular x and y axes that cross at the origin.
Good stuff.
And then we defined the x-coordinate or abscissa and the y-coordinate or ordinate and how the order in the xy pair really, really matters.
Yeah.
And finally, we saw how the axes create those four quadrants, and each one has its own rules for what the signs of the coordinates will be.
Great summary. And this brings up a question for you, listener. Like, now that you know how to locate a single point precisely, think about how we can use this system for more complex things.
Ooh, I like this.
Like, how can we describe lines or shapes or even movement on this plane? What are all the new possibilities this simple concept opens up?
Yeah, it's pretty amazing to think about, and that's something we'll be exploring in the future, so stay tuned for more.
For sure. It's going to get really interesting from here.
I can't wait.